All right, today we're going on a hunt, but not for anything you'd expect. We're searching for a ghost star, a completely hypothetical object that might just hold the key to one of the biggest mysteries in all of physics. So let's just jump right in with a pretty wild idea. We all know dark matter is everywhere, right? It makes up most of the stuff in the universe. But what if it wasn't just some big diffuse cloud floating around? What if it could actually clump together, collapse under its own gravity, and form stars, dark matter stars? Okay, so here's how we're going to tackle this cosmic detective story. First, we'll take a quick tour of the universe's weirdest objects. Then we'll zero in on our prime suspect, the Axion Star. We'll dig into where this idea even comes from, how scientists are actually trying to find these things, and then the big one, why finding just one would be an absolute game changer. So before we get to our main event, our ghost star, let's set the scene a little bit. Think of the universe as a kind of cosmic zoo. And trust me, beyond the things you've heard of, like black holes and neutron stars, physicists have imagined a whole menagerie of bizarre objects, each one stranger than the last.
And this is where it gets really interesting. You've got all these exotic ideas floating around. Stars made of strange quark matter, stars powered by dark matter just annihilating itself, even objects that would only exist if our theories of gravity are wrong. But in this incredibly crowded, weird zoo, our Axion Star really stands out. Why? Well, it's not made of any particles we know, and it has this unique habit of, well, exploding. That makes it a really compelling thing to go looking for.
All right, now that we've seen the lineup of cosmic weirdos, let's bring our prime suspect into the spotlight. It's time to properly meet the Axion Star. So what exactly is an Axion star? Well, at its core, it's a star made entirely of axions, which, by the way, are a top contender for what dark matter is. Now, these things form through this wild quantum process called Bose-Einstein condensation. You basically cool these particles down to almost absolute zero, and they all just clump together, acting like one single giant particle. Gravity pulls them in, but here's the kicker. They're not on fire. There's no nuclear fusion like in our sun. Nope. They're held together by the super weird dynamics of something called a scalar field. Think of it like an invisible energy field that's everywhere in space. And get this, they apparently come in two completely different flavors, and the difference is just staggering. On one end of the spectrum, you have what are called dilute Axion stars. These things are massive, fuzzy clouds that could be as big as an entire galaxy. Seriously. But then on the other end, you have dense Axion stars. These are super compact, maybe the size of an asteroid, and here's the important part. They're unstable. They can just poof, explode. The sheer difference in scale is just, it's hard to even wrap your head around. Okay. I see an equation, you see an equation. Don't panic. You do not need to solve this. Just think of this as the architectural blueprint for an Axion star. It's the cosmic code that describes how it can even exist. It's this beautiful, delicate dance between quantum mechanics, gravity, and field theory, all packed into one line of math. But that leads to a pretty big question, right? Is this whole Axion star thing just a fun idea that physicists cooked up with some cool math? Or is it actually rooted in something real, something solid in our understanding of the universe? Yeah, let's put it this way. Are we just talking about a wild guess here, a mathematical curiosity? Or is the Axion star something that our best, most fundamental theories of the universe actually predict should exist? And this is the really crucial part. This isn't just some random idea. As you can see here, the axion particle, the building block of our star, just sort of falls out of theories, like string theory. You see, for the math in string theory to work, it needs all these extra dimensions and symmetries, and it turns out a natural consequence of that is that the axion has to exist. It's not something they tacked on at the end. It's a feature, not a bug. That gives this whole idea a really, really strong theoretical pedigree. Okay, so the theory is solid. It's not just a wild guess. And that, my friends, brings us to the really exciting part, the hunt. I mean, how in the world do you even begin to look for an invisible star that might be no bigger than an asteroid, potentially millions of light years away? Well, believe it or not, there's a plan. This isn't just wishful thinking. It's a real, multi-decade international effort. Right now, telescopes like CHIME are already on the lookout for strange signals. In the near future, the incredible Square Kilometer Array, the SKA, is going to join the search in a big way. And then, looking out to the 2030s, the LISA Space Observatory is going to open up a completely new way to listen to the cosmos. So, how do we spot them? Well, the main method is pretty dramatic. Remember those dense asteroid-sized Axion stars? If one of them happens to drift too close to something super dense, like a neutron star, the gravity can basically rip it apart. It destabilizes and detonates. And in that detonation, it unleashes this incredible blast of energy, a flash of radio waves that lasts for just a millisecond. We call it a fast radio burst, or FRB. And telescopes like CHIME and the SKA are scanning the skies for exactly that kind of smoking gun. The second method is a bit more subtle, a bit more elegant. If two Axion stars were to spiral into each other and merge, they'd create ripples in space-time itself, gravitational waves. Now, we've seen this from black holes, but here's the telltale difference. Because Axion stars aren't black holes, they don't have an event horizon. So when they merge, the gravitational wave signal would be missing the final part, the ring down, which is kind of like the sound of a new black hole settling down. And the LISA Observatory is being designed specifically to listen for that missing echo. So all of this decades of work, billions of dollars poured into incredible technology, it really brings us to the final and most important question. Why? Why does this matter so much? Why is finding just one of these ghost stars worth all this trouble? Well, because, as one source puts it so perfectly, the Axion Star is, and I quote, the exotic star most likely to rewrite physics by 2040. I mean, wow, that is an unbelievably bold claim. And here's why that claim isn't crazy. Finding a single confirmed Axion star would solve not one, but two of the absolute biggest puzzles in fundamental physics, all in one shot. First, boom, we'd finally know what dark matter is made of. And second, it would be the first ever piece of hard experimental evidence for string theory. It would be a revolution. And a path from where we are now to that revolution is actually surprisingly clear. It all starts with one signal, just one. Confirm a single candidate, whether it's a specific radio burst or a weird gravitational wave, that perfectly matches the profile. That one single detection would instantly take Axion stars from this speculative what-if idea and make them a standard part of our cosmic model. And from that moment on, we start rewriting the textbooks.
And here's the final, truly tantalizing thought. We might not even have to wait for these new giant telescopes to come online. The very first clue, the one signal that kicks off this entire scientific revolution, it could already be here. It could be sitting right now, completely undiscovered in the massive archives of data we've already collected.
Which leaves us with one last, kind of mind-blowing question to think about. Is it possible that the answer to one of the universe's greatest mysteries, the secret of dark matter, is already on our hard drives, just sitting there, waiting for someone to find it?